Okay, so hello everybody. I think I'll make a start now. So the agenda for today's session is I'm going to talk a little bit about OpenACC, and then I'm going to hand over to Luca, who's going to do a walkthrough and discuss some of the practical solutions to the practical exercises. Okay, so as usual, please feel free to post any questions in the chat window as we go along, and I'll do my best to keep an eye on that and answer them as we go. Okay, so yeah, having heard everything about programming GPUs with using OpenMP directives, I'm just going to talk a little bit about OpenACC. Say it's if you see, because you've seen all the OpenMP stuff, then the OpenACC is very similar. So what I'm really going to do here is point out the differences and explain how the two different APIs relate to each other and translate to each other. Okay, so as an overview, OpenACC is an alternative directives-based API for offloading to devices. It actually predates OpenMP offloading, but now these days it has fewer implementations than OpenMP offloading does. So there are fewer compilers now that support OpenACC compared to OpenMP or offloading. For offloading, OpenMP and OpenACC have very similar functionality, though OpenACC is a little more GPU specific. So OpenMP offloading was designed to be usable on other types of devices. There aren't very many interesting ones around at the moment. But OpenACC was really targeted at GPUs only. So OpenACC uses different terminology to describe the sort of hardware abstractions, and it also uses different syntax. In contrast to OpenMP, OpenACC does not control any parallelism on the host CPU. So with OpenMP, you can use the regular OpenMP to do multi-threaded programming on the CPU, as well as offloading to the GPU in the same application. So OpenACC doesn't do anything on the CPU side. So it assumes that if you're going to do parallelism on the CPU side, then you're using some other API. And in terms of the philosophy, OpenACC has a slightly less prescriptive approach than OpenMP. When it was designed, it was intended to rely a bit more on the abilities of compilers to analyze code. Whereas the philosophy from OpenMP was always, well, OpenMP is very prescriptive. You as a programmer specify what you want. And the compiler you're not relying on the compiler to do anything like data dependency analysis or auto parallelization. That emphasis in OpenMP has slightly changed. Okay, so as you see with the OMP loop directive is slightly more towards the let the compiler do what it wants approach, but OpenACC from the start had this idea that for in some cases you can just rely on the compiler to do the right thing. Okay, so the syntax is very similar to OpenMP. It uses directives in exactly the same kind of way. It's just that the characters that form the sentinels at the start of the directives are different. So for Fortran, it's $ACC instead of $OMP. And for C and C++, it's #pragma ACC instead of #pragma OMP. And in terms of the execution model, so in the same way as OpenMP does, OpenACC exposes 3 layers of parallelism on the device, though for the most part, we typically only use the first 2 for programming GPUs. So where OpenMP talks about teams, the OpenACC terminology is a gang, and that's what's basically being mapped to an SM in the GPU. OpenMP talks about threads. The corresponding term in OpenACC is worker, and that corresponds in the hardware on a GPU to a hardware thread within an SM. And the third possible level of parallelism is, so in OpenMP, that would be SIMD, which we haven't talked about very much in this course because it's not really particularly useful for GPUs. In OpenACC, the terminology is vector, and that would on the hardware that would correspond to a vector instruction in a single thread. So if we think about execution on the device, then the ACC parallel construct is the basic offloading mechanism in OpenACC. Okay, so during execution, when an ACC parallel construct is encountered, the code it contains will be executed on the device. And by default, the code inside the ACC parallel construct is executed by every gang. Okay, so that's different from OpenMP. So really, ACC parallel, the closest equivalent would be OMP target teams. So if you really want serial execution on the device, then you can do that. You can specify ACC serial, and that will do serial execution on the device. So, but by default, execution is essentially a replication on one copy of that block of code on every gang. That means one on every SM in practice. Okay, so as you'd expect, this is what the syntax looks like. You have #pragma ACC parallel, and then a block of code, typically in curly braces here, which will be executed on the device. And the same for Fortran, ACC parallel, block of code, and N parallel. So it looks, syntactically, it looks very similar to OpenMP. The structure is very similar. It's just that the actual spelling of the directives is different. So for data transfers, okay, so these clauses on ACC parallel or other directives work in a very similar way to OpenMP. So it's basically the same idea, only the syntax is different. So the correspondence is, so for OpenMP, if you have map2, then the OpenACC syntax is copy in. Map from an OpenMP is copy out. Map to from, so going both ways to the device and back to the host again, is copy. And alloc, where you just want allocation on the device and no actual data values copied, that is the corresponding thing in OpenACC is create. Then we also have the equivalent for data regions. So structured and unstructured data regions and updates also work in exactly the same way as in OpenMP. So again, the corresponding syntax is of OMP target data corresponds to ACC data, and then the unstructured version, you have target enter or target exit. You have ACC enter data or exit data. And then the updates, so OMP target update 2 corresponds to ACC update device, and OMP target update from corresponds to ACC update self. So just a simple example. If you want to do some data movement with these clauses, you could say, okay, hash pragma ACC parallel, and then copy in B and C. So that will copy 2 from the host to the device, and copy sum here will copy both ways. And the same idea for Fortran. So in OpenACC, the ACC loop construct can be applied to loops to specify parallel execution on the device. This doesn't quite exactly match the semantics of OpenMP of OMP loop in OpenMP. ACC loop is somewhat more prescriptive than OMP loop. And then you can specify at which levels the loop should be parallelized. So you can specify one or more of the parallelism level, so gang, worker, or vector. And then things like collapse for dealing with nested loops, reduction variables, and private variables. Those clauses also work just the same as in OpenMP. Okay. So the corresponding would be, so if you want to parallelize a loop across teams in OpenMP, it would be OMP teams distribute. In OpenACC, it would be ACC loop gang. Parallelizing a loop within a team, across the threads within a team, would be OMP parallel for or do, depending on whether it's C or Fortran. So that would correspond to ACC loop worker. And if you want to do loop over vector instructions, then OMP SIMD would correspond to ACC loop vector. And so the usual thing, OMP teams distribute parallel for would correspond to which will parallelize the loop across both levels. So the corresponding thing in OpenACC would be ACC loop gang worker. Okay, so if we return to our favorite example of offloading this loop, okay, so what we'd want to do it in OpenACC would be hash pragma ACC parallel loop gang worker, and then the copy in B and C, move the data, copy sum to copy the initial value of sum in and the final value of sum out at the end, and need to specify that we're parallelizing the loop, then sum is a reduction variable with respect to the loop. Okay, and exactly the same in Fortran syntax. So OpenACC also has this feature called kernels. So it supports a more hands-off approach to offloading with the ACC kernels construct. So what this does is it specifies a block of code which can contain pretty much anything. It might, can potentially contain multiple loops, so not necessarily nested inside each other, multiple loops one after the other, and other statements. And the entire block of code is intended to be offloaded to the device. And it leaves it up to the compiler to decide how to do that. And typically each loop nest will actually be translated into a distinct kernel. Okay, so you'll get a separate, you will in practice generate a separate offload for each loop nest. And then you can also leave it to the compiler to automatically generate the required data transfers, or you can specify them explicitly. So this is very hands-off approach. It's just leaving it pretty much. You can leave it pretty much entirely up to the compiler to decide what to do. But of course, if you do that, then there's no guarantee that the compiler will actually succeed. Okay, so you can potentially end up with extremely disappointing performance where the compiler decides to offload the code but execute it sequentially on the GPU on a single thread. So it's possible to silently generate terrible performance with this, as well as potentially doing on the other hand, sometimes in simple cases it'll be perfectly happy and it'll do a decent job with minimal effort from the programmer. So there's the usual kind of two sides to this very sort of rather high level approach. When it works, it's great. When it doesn't work, it's terrible. So this doesn't really have a direct counterpart in OpenMP. Okay, so the closest equivalent would be something like OMP target teams loop, but that only applies to an individual loop or loop nest. So that would be the sort of kind of closest equivalent. So you can simply just identify the pieces of code that you want offloaded, decorate it with hash pragma ACC kernels or exclamation mark $ACC kernels and N kernels in Fortran, and then just leave it up to the compiler to decide what to do. Okay, so it'll make the decisions about how it parallelizes the loop across SMs and across threads within the SM, and how many gangs and workers to create, and it'll also take care of the data movement, and it'll recognize, the compiler will recognize that sum is a reduction and do that all correctly for you. So at least it will do it'll work fine in simple cases like this. So just as in OpenMP, we also have to take care of what happens if we want to call routines from inside an offloaded piece of code. And similarly, we have to specify to the compiler that we want a version of that routine compiled for the device. So routines called from inside offloaded regions have to contain an ACC routine directive to indicate that the compilation for the device is required. So that's equivalent to OMP declare target in OpenMP. So it goes in the same place as in OpenMP. Okay, so before the routine specification in C and C++, or inside the routine in Fortran. However, it's a slight difference. There's no equivalent to end declare target in C++. So each routine has to have its own separate ACC routine directive. You can't just group them up and into a batch like you can in OpenMP. So you can also specify a clause which is either gang, worker, or vector to indicate the level of parallelism that's going to be exploited in the routine. So you're supposed to use ACK routine gang if the routine contains an ACK loop gang directive, for example. In terms of synchronization on the device, so ACK atomic directive is exactly the same as OMP atomic. It protects the memory location on the left-hand side of the following statement from race conditions. And just like OpenMP, it has read, write, and capture variants as well as update, which is the default. So that's exactly the same as OpenMP. However, unlike OpenMP, OpenACC does not support other synchronization constructs such as OMP barrier or OMP critical within a team or a gang. So the equivalent to those things don't exist in OpenACC. And if we want to think about asynchronous offloads, so again, as with OpenMP, offloaded code constructs in OpenACC are blocking on the host by default. So when we do an ACK parallel, the thread on the CPU that called that will block until the offloaded code has completed. So again, you can change that behavior. And in OpenACC, the asynchronous offloads are enabled with the async clause, and then there's an ACC wait directive to block the host until all previously issued asynchronous kernels have completed. So that's equivalent to OMP target no wait and OMP task wait to do the blocking in OpenMP, but OpenACC doesn't support a full tasking model on the host. So there is no equivalent to, you can't do dependencies between offloaded regions like you can in OpenMP with a depend clause. On the other hand, though, OpenACC does explicitly support multiple queues on the device, which OpenMP doesn't. So it's slightly different, and again, this difference comes down to the fact that OpenACC is explicitly designed for GPUs, whereas OpenMP is not. So you could do something like this. You can do, if you want to do asynchronous offloads, you can do hash pragma ACC kernels async. So this loop will get offloaded. The host thread that reached this point will carry on and potentially do some computation on the host at the same time, and then at some point later you can have a hash pragma ACC wait directive to force completion of the kernel before the host thread continues. Okay, and OpenACC has a slightly less rich set of runtime execution routines. So there are some equivalents though. So get num devices has an equivalent, has a direct equivalent in OpenACC, as does get device num. If you want to control the number of teams and number of threads, then the only way there are no routines for that. The only way you can do that in OpenACC is with the num gangs and num workers clause on the parallel or kernels construct. Okay. And there isn't an equivalent of get team num, for example. So there are some things which are possible to do in OpenMP which you can't do in OpenACC. Okay, so that's really a quite quick tour of OpenACC and the differences from OpenMP offloading. So in general, my advice would be that if you are developing a new code or porting a new code to GPUs, then it probably makes sense these days to use OpenMP rather than OpenACC. OpenMP offloading implementations have improved and matured quite quickly over the last year or two, to this state where there's really you really aren't going to see any significant performance differences between OpenMP and OpenACC anymore. Okay, that wasn't true in the past because OpenACC implementations have been around longer. And were more mature. So in the past, there were performance arguments for using OpenACC over OpenMP, which have largely now gone away. And OpenMP is the specification which has more support across different compilers and devices. So that's probably what I would recommend that you use if you're porting a code now. However, it might be, you might come across, you might be presented with a code that contains OpenACC directives. So there are still, there's still a bunch of them out there. So if you need to understand or modify a code that's got OpenACC in it, then you need to know what it means, or possibly you might want to, if you've got OpenACC code, you might want to then port that to OpenMP. That's usually a pretty straightforward process, and now you know the equivalent things to and the way to do the translation. So Chen asks, will OpenACC die out from the marketplace, and will OpenMP finally win? It's a good question, and I think that the answer is yes, but okay, and the but is because it's not really an open marketplace. Okay, in particular. In the US, Exascale program invested pretty heavily in porting codes to OpenACC. So the compilers are going to compilers will carry on existing in OpenACC. Compilers will carry on existing in order to be able to support some important existing applications. But in terms of the OpenACC specification isn't likely to evolve any further, whereas OpenMP will. And my guess would be that you won't see any, you're unlikely to see any new implementations of OpenACC in the future. Okay. So what currently exists will probably persist for quite a long time to support existing applications, but you won't see much development or of OpenACC, either in terms of new features in the specification or in new implementations in compilers. Okay, does anybody else have any questions? So Liam Parsons, is there any interoperability between OpenMP and OpenACC? Well, that's entirely down to the implementation. So I think, for example, if you use the NVIDIA compiler and you try to mix them both in the same code, I think that would probably work. Yeah. But there's nothing formal, okay? There's nothing in either specification that says it has to work or how it should work with the other one. Yeah, it is possible. But you're just relying on a particular or a particular implementation like the NVIDIA compiler for it to work correctly. It should, yeah. So I guess that's kind of useful if you're doing a translation, because you can do it. You can, if you wanted to translate OpenACC to OpenMP, you could potentially do it, do it piecewise and still have a working code in the middle. Anything else? Yeah. Yeah, that's true. Yeah. And so, yeah, if you pick the right compiler, then you can do it like that. Okay, so if there aren't any further questions, then I will now hand over to Luca, who's going to talk through the practical exercises for you.
Thanks, Mark. I'll now share my screen. All right. Is everyone able to see my screen? Perfect. Going to try to make it a bit bigger so everyone can see. So we're going to go run through essentially 2 of exercises. So we'll get back into the land of OpenMP and try to use OpenMP to essentially offload our CPU code to GPU. I'm going to demonstrate mostly the C versions. The Fortran version are similar in concept. The syntax is slightly different, and there are some features that do not really work with the Fortran compilers we have. So that's why if you've seen the personal exercises, the Fortran version has some less points than the C version. So we start with the pi exercise, which is relatively simple. So we want to, in this exercise, we want to compute pi, and we essentially do it by sampling some random points inside a circle. and then looking at the ratio of those that falls inside and those that falls outside. So we need to offload it to a GPU. So we need to add our OpenMP directive. It has to be on the GPU, so we can put target on it. I've already set up my environment, so I can type make to run it. Now I need to run on the GPU. Just to make it simpler, I've just have an alias for a command that submits to a cluster. Hopefully there will be GPU available. If not, I'll just show the solution. So let's run it. Okay. Let me clean it because I don't think it actually compiled. Okay. Let's first, just to compare, let's first run it on the CPU only. Okay. So we ran it on the CPU only and it took about the other 6 seconds. Target. Oh, I'm going to request some resources again. Done. And clean and recompile. Now I'll run it. Okay, we see that it did nothing, by 0. That's probably because we're doing a computation on the CPU, but we're doing a reduction of a sum, and we're never getting it back to the CPU. So you're probably doing nothing actually. So because it's a reduction, we can use a reduction clause. So we specify the reduction, compile again, and run it. And now it hangs and takes ages. So what's happening here is that we told it to execute all of this on the target. We specify that it's a reduction. That's because all the threads are doing a reduction of the variable sum. But we also need we also need to get it back, but the default behavior is that when we specify a reduction is that the resulting data is sent back to the CPU. So we don't need to do any explicit mapping here. Okay, so it finished and it took 43 seconds. That's because adding just target, everything runs on a single thread on the GPU, which is extremely slow. You're not using any of the bandwidth on the device. You're just using one thread, so you're completely limited by the latency. So now we can add teams and distribute the iteration across teams. We recompile, run it. So now we're spreading all the iterations to different computing units, but inside a different computing unit, we're still using just one thread. So that means we're only using a very small fraction of the GPU, one thread per computing unit. So essentially 104 threads instead of over 200,000. So that means that it's faster now than the CPU, but just by one CPU thread, but just by a factor 2. And the GPU is far more expensive than one CPU core. So now let's add finally parallel for. So this means to distribute the threads, all the iterations in the loop across different threads inside inside the CPU. So you can use all the computational unit on the device. So we compile, run it again, and okay. Now we can see that this is much faster than what we did before, because we are actually using all of the resources available on the device. Are there any questions about this before we move on to the much more complicated exercises, which is porting a Poisson solver? Okay. If not, I'll move on to the Poisson example. So exercises. So I'm going to show the C++ version again. I already have, I'm going to clean our results from past simulation. Okay, I'm doing make clean and compile. Oh, I need to set up my environment, and I can do that by just sourcing the file. Okay, now I'll go back to the example. Okay, clean and compile. So now we can run this on the GPU. And this runs, you can see this numbers get smaller and smaller. Eventually, when converged, you expect that to become nearly zero. And it took about 800 milliseconds to run. So this is entirely on the GPU. So now what we want to do is to put this on the to port it to the GPU. So as the instruction says, you will look in the Jacobi.c++, and you have this loop. This is the loop you want to port to OpenMP. So we need to make it parallel. So we do the same thing we did before. So add a pragma, MP, distribute over teams, and then distribute or across iterations. And compile again. Might take a bit of time in the linking phase. So now it's done. So now going to try to run it. What do you think will happen? Do you think this will work? So let's try it. So as you see, we have distributed all the data. So we have distributed all the iterations between across the loop. What else do we need to do in general? We need to distribute the task. Yeah, correct, Jonathan. We are not doing any data mapping. Now, some data mapping is done by default for you. So in general, it might just work. We didn't need to do any data mapping in the by example. But this is more complicated. So let's run it. So this was so. This should not have worked. Let me recompile. Might have forgotten to recompile. Okay. What's going on? Let me check. Is it working? So what's expecting a set false? It's actually not guaranteed to, because anything can happen. Oh, that's why. I forgot the target. So this was executing on the CPU, was essentially distributing on the CPU. So this is also something to always check, which is where things are running. So OpenMP will, if it can't offload to the, so if you forget the target, it will, it's likely that it will work on the CPU as well. Although it probably won't do the things you want it to do, but it's legal. I probably will not discretize in an efficient way. So let's try again. Okay. And you see there's a memory access fault, which is what we were expecting. Okay, so we need to map. Now this is a bit more complicated here. So, well, we can do it on the same line. So we can use map directives in order to do all the mapping. So map, we need it to tell it how we're doing the mapping and our use communicating data. So here you want to send to the GPU, but you also want to get the result back at the end of the calculation. So we use two from. So send to the GPU and the end of the parallel region, so the offloaded region, then get the result back. Now the tricky bit is to map everything. Now in a real code, this tends to be a bit hidden away. You'll have some derived types, so class structure. So you can see here we are accessing the variable g, which contains the grade. So this is essentially a struct, if you wish to see. and then there's some standard arrays of CRAs, one-dimensional arrays. So we need to map everything. So we're going to need to map n. So n specify how many grid points there are. So you can find out by looking, you can see that this is an object of type grid type. And if you do a search across the files, you'll find that this is defined in this grid.h file. And you see this is a struct that contains various elements. So all of these will need to be mapped to the GPU. So let's map all of those. You have G, so you have to access those elements. For those of you who are for Fortran, this just means just a notation to access the members of this data structure. It's an array of size 2 because it's a two-dimensional system. So we tell it to start at 0, and we map 2 elements. And we need to do so for all the other elements, all the other pointers in it. If it's color, the default behavior will be correct. But if it's pointers, it will just be mapping the pointer itself, so the address itself, and not the data it's pointing to. So we need to do it explicitly. If you're using Fortran, this is much simpler, because Fortran, if you use standard arrays, they contain information about the size. So that means that the compiler can easily figure out how to do automatically the mapping for you, because there's all the metadata information about how big the array is or its shape and so on. So if you have an allocatable array, it will be mapped as you would expect it. So the whole array gets mapped. But pointers do not have that information, so the compiler can do it. So you have to explicitly tell to map everything. Okay. And then we need to map the field. So we have field, so there's various field that we're accessing here. So there's filthy new and filthy old. So filthy new is the new field that is being accessed, which is being set, and we need to specify the size, and we can use the get size method, or you can just use you can just multiply the two values in M to get the size. And we need to do the same field old. And field O. I think that's everything, but let's see. Compile. Let's see if it runs. Looks like it. So you can see that it's running. It's running on the GPU. Okay. And it took 1.3 milliseconds per iteration. You might have seen, if you run it the CPU only version on one thread, it will take about 0.7 millisecond per iteration. That means it's much slower than one CPU thread, which is terrible. Okay. So, but this time we have all the target teams distribute parallel for everything. So why do you think the performance is so slow? So we're running this kernel multiple times, and every single time we're doing distributing all the iterations in the loop across the GPUs and doing the data mapping. And we do it lots of times. What do you think? Why do you think this could be so slow? Okay, so Jonathan, you say that you're copying too much data. You're right. We're doing a data mapping every single time. So we're transferring at every iteration. That's not really needed because every time we recompute the Laplacian, we just need the old data. It's already on the GPU, so there's no need of doing all the data movement. Liam, you say, well, we don't have enough parallelism. You're probably right. We are parallelizing only on the outer loop, but not on the inner loop. So we could do better. Okay. However, data transfer is really, really slow. So this is probably the bottleneck here. So what's really killing you is probably all this data mapping. So in order to improve, we need to do it only once. So you still want to have to do all the data mapping, but you do it once at the beginning, then you run several times this kernel with all the data on the GPU, and only at the end, when you do output, you get it back. So let's comment this out. Okay, I'll recompile. Now, nothing is mapped here, so this will not work. So now I'm going to take, as told in the exercise, I'm going to look inside this folder, then look where the calculations are. I'm going to move this to the right. You don't really need to see that anymore. And so here is where your computation is. Output is done here. So we will need the data at this point. And we need to send the data here. So this is why we need to do all the data mapping. So let's do it. And we're going to map the same data only once advanced. So it's exactly the same quantities. We're just doing it from a different file. So we do have multiple fields. So we'll need to map all of them. So we're going to need a loop over all the fields. And then we're going to need to send all the data. So which directive do you think here is useful? So we need to send to the target. Now we're not doing anything here. We're just sending data. So we'll need to enter a data region. And then we need to add the map directive. And then there are paths, which is mapping everything. Now here we're only sending data to the device. We're not getting it back. We just need to send everything and then do all the work on the device. And once we're done, get the results back later, once we've finished processing. So we're just sending to the device. So we're using the to modifier. And then we have to remap everything we did before. So current grid, you need the shape. Is it? Yes. And everything else, like we did before. So current green, so the X, start. So you can see all this is very error prone and also quite laborious because everywhere you have to include all the fields. Okay, so I think I have accessed all the elements. And then let's look at the fields. So the fields here, I need to look what's inside the field. So that's the data structure. And you can see it has data and size. So this is a scalar, so it will be mapped by default correctly. This will not. So we need to map it. So which one do we have? So we have new. So this, because we have different fields, it was actually a vector, so we need to access that vector, access the data. Okay. I'm just going to put in parentheses just for safety. So we know that this applies to all this. And then map with the current size. Okay. Does this compile? Check. Nope. Remember call size. Yes, this was get size. Okay, looks like it's going. So let's go to the rest of the fields. So this was the new, and we have the old. The data. Looks like some parentheses that were gonna miss. Come. See new, see old. This looks good. And there was a third field, which was called, oh, so that's the say the density. Okay. So hopefully it should be everything. Okay, we've messed up with parentheses. Oh, yeah. Should need to map, yes. Oh, I think this was on a separate line. Okay. You can see how this gets quite ugly with lots and lots of entry. Okay. Now let's run it. Okay. So we've mapped everything, but we're still running on the CPU. So you see this is the same time on the CPU. So Jonathan, you said, does this seem difficult? Yes, it is. And yes, there is a way. And we'll get to that in a bit. There is a way to get it easier. So here we commented everything out, so we're not running on the GPU. I'm going to get rid of all the mapping, but I'm still going to send to the GPU. Going to run. Okay. It did not cache, but you see everything is zeroed here. Anyone knows why that could be? What did we do wrong? So it didn't cache. So luckily, we didn't forget anything. So here we're looping over the fields, and for each field we're sending all the data to the GPU. Then we do some processing, and then do up. Yeah, correct. Correct, Jonathan. So we need to get the data back. So all the computation is here. Output is here. So this is the right place to get the data back. So I'm going to just copy over all of this. The difference is instead of enter, I'm going to write exit. So you want to get the results back. And because we're getting from the GPU, we need to use from here. So the rest should be the same. So let's compile and run it. Okay, so it looks fine. So the results seem to be the same as before. And now you can see it's still slow, but at least we're faster than one CPU thread. So it used to be 700 microseconds. Now we're more in the 400 microseconds. It's still awful. Hey, but it's better. That's because we're not doing all the mapping once. Because we're no longer doing the mappings at every single iterations, so we're getting it that is about 3-4 times faster, just by making sure that we minimize the amount of data movement that we do. Now, all of this is, as Jonathan said, this is pretty ugly. So how can you make it something simpler? So there is a way to do this. So the idea is that you really don't want to rewrite the mapping explicitly every single time. So the way you will do it, you want to actually declare or you do the mapping of a struct and do it only once. So the way you do this, you can do pragma-mp, then declare map, and then you can use. So what are we declaring? We're declaring a mapper. So the mapper will act on a class, a struct of a certain type. For instance, on the field. So field type, and then we just give it a dummy argument. Now we have to tell OpenMP how to do the mapping of the struct. So we can do map. And what do we want to map? We want to map F, so the field F, and what's inside of it. So here we can see that the field only has, so we want to map its data members as only data and size. So we can map F dot, so the data. So this array, so we need to know the size. Fortunately, there's a get size method, so we can just call that in order to get the size of the field. Okay, and then we try again. Well, try again. So here we're mapping the field F, but we also want to map the grade. So we can do pragma-mp, declare mapper, the object, so the object of that grade type, dummy argument, and then map. And then we tell what to map. So we want to map G dot, and then all data elements. We've seen them before, so I'm just quickly writing it. So there was G.dx, G.start, and G.end. So the idea is that you do it once when you write your struct. So you write your struct and then you declare a mapper for it. And probably write some unit tests to check that when you're using the mapper, everything is being mapped correctly for your struct. If you have another struct, you do it again. So this is much simpler because you do it once for one struct, and you just make sure not to miss any data member that does not get mapped correctly when you do it automatically. So basically anything that is an array, so any pointer. Okay, let's compile and see. Okay, it did compile. It did not complain. So now we actually have to use those data mapper. So we go back to where all those early definitions were. Okay, I'm just going to read all of this. And now I'm going to map my arrays of fields and the grid. So I'm going to use a target directive this time. So MP target, as usual. We're not doing any computation. We only really want inside this for loop, we want the data to be available on the device. So we have the data directives. Okay, only data. No, I'm not telling anything about where it should run. Use the map directive. Now I want the data to be mapped, so to be transferred to the GPU, the beginning of this block, and I want to get it back here for the end of the block. Don't need to do enter. I can just use the data directive, and this will apply to the whole block afterwards. So essentially they will for block this for loop, which is what I want. Perfect. So I use to from. So send to the GPU, do several iterations, and then get the value back. Now it's an array, so I want to map the array of new fields. But I've already told OpenMP how to map a field type object. So I just have to do the normal mapping for an array. So I have to specify where the array starts, so at the beginning, so index 0, and then the size of the array, which in this case is just the number of fields. And then do the same for field. And density. Cool. And then the grid. From, I'll delete all this thing. Compile again. Hopefully I won't make a mistake. Let's run it. Okay. So it runs. Looks okay. Performance is the same as before because we're doing the same thing. We're not doing anything different. But this time it's much more concise. Instead of the garbage of fields inside of it, you just straightforward mapping of 3 arrays and 1 variable, and that's it. You of course have to remember to declare the mapper here, but this is still much easier to keep track of. So this makes your life much easier if you're using C. If you're using Fortran and you're using and you're not using C pointers, you really don't need these features. And as far as I've seen, most Fortran compilers, well, the mappers don't work, as in they're not implemented. They're part of the standard, but they're not implemented. So as long as you're not, essentially, as long as you're not relying heavily on Fortran or C pointer, in Fortran, the mapper will do the right thing. It will map all the arrays for you. So you don't really have to bother. If you are using C pointer, you will need to do the same strategy. Assuming you have a compiler where it's actually implemented, which is not the case of a Cray compiler. So if you try to use mappers on Fortran, on Cray, the code will not compile. It will complain that unknown directives or something similar. Okay. For interest of time, I'm going probably to skip over. Well, no, it's very easy. So we've done all the mapping, and I have a different implementation using OCaml. So I can compile using OCaml. Okay. However, I've not done any data mapping, so I don't expect this to work. So we'll first tell you where to find this, which is in Jacobi heap. So the implementation is heap.cpp. Okay. So here essentially I have a function which is using heap to do the same. So we're not using OpenMP, we're using heap. The problem is heap expects pointers to data on the device. But the problem is you don't have access to them directly in OpenMP. In OpenMP, you just have a variable that has different meaning whatever you're running on the CPU and on the GPU. So how can you tell heap to use the address of a variable on the device and not on the CPU? Because you only have one variable anyway. So just taking the address will not work. So we have to tell it how to do it. And fortunately, we've seen that there is a directive to do that. So pragma-mp target. Again, no computation with just data movement. So we need to add data. And then essentially use the keyword use device address. And then you have to tell it, okay, this data is already on the device because we've mapped it, it's mapped. You just have to tell heap, use the address on the device, not the one on the host. So you can just use device address and then tell it what we map, what are the pointer. So you can use the same notation you use for mapping. So this is similar to what we've seen before. So this is just a straight array. So we map it in the same way we've seen in the inside Jacobi. So we have to map all the fields. So I'm going to map field C old, start at 0, and a size G get size. And there's also a field called field row. Field row on 0 to G get size. Did not compile, but did not compile the right thing. So my post can. So let's see if this will work. Oh, wrong executable. Oh, okay, something did not get mapped correctly. Filthy new is filthy old. Oh, the gate. So we also need to map the gate. G0. I'm going to map the gate as well. It's a pointer, so I'm just going to declare it as an array of size 1. Try again. And this works. Infinite is much faster. But it's not really a fair comparison because the degrees of optimization are not the same. But this is, in general, this is a reason you might want to have a heap kernel instead of an MP program is because it can be much faster. Because you have more degrees of control. So running, so you might want a kernel which is really important for performance because it's where your application spend most of the time. So it might make sense to do a specialized heap or CUDA version, so for specific GPU vendors, and optimize very well those versions, and then just link it to the rest of your program. And you can do this using each device address and each device pointer to go the other way around. Okay, this was a bit of an interlude. So we're going to go back to our OpenMP versions. Run it again, just to check we haven't broken anything. Perfect. Now we saw that we have different fields, and you might think that it might be quicker and faster to submit all these fields in parallel to a GPU. So to do that, we can, let's open the Jacobi file with implementation. So we have different fields, and we're offloading a parallel region for every field, but we have multiple fields. So what if you want to do them in parallel? So you have different fields, I need to process different fields, and I need to take this parallel region, offload it to the GPU, then don't wait, just go to the next, offload that to the GPU, so offload all the fields to the GPU, and then wait for all of them to be finished. Anyone, any idea how you could do that? How can you do that in a... Okay, that's a good idea. That will make it faster. However, it will not make the different parallel regions, so one for every field, running parallel to the GPU. It will just do each one at a time. Take field to 0, offload to the GPU, While for it to finish, then perfect. Perfect. So as Jonathan said, we want to use the asynchronous feature in OpenMP. So we can add no wait. We need to add synchronization. So once we're done with all the fields, we need to add a task wait. So that's to synchronize the GPU and the CPU. Okay, let's compile. Let's see if it likes it. Looks like it. Okay, so now all of these, you would expect, what we're telling OpenMP is all these different parallel regions, you can tag them and offload them in parallel to the GPU. And then once they're all finished, keep going with the next loop iteration. Okay, so let's run it, see if it works. Okay, data looks correct. Okay, performance is essentially the same as before. But okay, we only have one field actually in this case, so let's increase it. So with one field, that you won't expect any difference. You need to have different fields in order to overlap between different fields. So I'm going to increase the number of fields. Let's put them to 10. Okay. And now run it again. Hopefully we won't have an error. And run. Okay. So all the fields are actually doing the same thing in this case, so which is a bit stupid. But in a real application, you can see how you might have different initial conditions for every field, so you'll get different results. Okay, so it's doing the 10 fields. That's taking a while. So let's stop this. I'm going to reduce it to 5. And let's try without using no wait first. I'm going to just comment out the task wait and delete the no wait. Okay, so this will be done sequentially. So every one field at a time. And I run it. Okay, so it's running all the fields. Now, this does not look much faster to me. So it should be the same speed we've seen before per iteration, but multiplied by the number of fields. So we get 2.11 seconds. Now let's do it in a asynchronous way. So let's add no wait and task wait. Okay, so you would expect it to be faster because you can overlap field. So it was 2 milliseconds, about 2 milliseconds per iteration. Okay, so this runs. And it takes 2 milliseconds again. So you'd expect that it's faster, but it will not always be the case. So there are cases where the kernels will actually not be offloaded as while you tell OpenMP that they can be offloaded asynchronously, does not mean that the compiler will actually do it for you. So this depends on the quality of the implementation. Now, turns out that the Cray compiler does a pretty bad job, so actually it doesn't submit to different queues. So GPU has different queues, which allows you to submit multiple parallel regions to the GPU at the same time. And if you try this, I've tried this example in NVIDIA compiler, and this was faster. However, the Cray compiler actually submits everything to the same queue, even when you have no wait. So in practice, they're still running sequential. But on other compiler, this will be faster. Now there is a way to do it faster too. So here we're only using one CPU thread, but OpenMP can use also multiple CPU threads, so there's no reason we can't use multiple parallelize over CPU threads. So we can add a parallel for. So we distribute the fields across multiple CPU threads. And then each thread is going to submit to the GPU. We're going to do it in the usual asynchronous way. So each thread will submit a kernel to the GPU and just wait. So each CPU thread will submit a parallel region and then wait for its parallel region to finish. And then there's an implied barrier at the end of the parallel for region. Okay. So let's see if this is better. Okay, compiled, let's run it. Okay, this looks a bit faster to me. Let's see. Yes. So it used to take 2 milliseconds, and now it's less than 1 millisecond. So asynchronous execution did help. But you need to use different threads. Now this will vary on compilers. So some compilers will be very good, very bad at doing this. So using multiple CPU threads and each thread submitting to a GPU. Other compilers are good at submitting to different queues. So it will depend a lot on your implementation. Possibly in the future, as compilers get more mature, they will be more similar in terms of performance. So asynchronicity can make things faster. How much faster will depend on the quality of your implementation. So beware your compiler. So now I'm going to return to the original version. So I think synchronous. So that's right, it's done. Okay. Just to make things a bit faster. And I'm going to return to one field, compile, run GPU, Poisson. Okay, so we got the 0.4, so that's about 400 microseconds. So now this is not that fast either. It's relatively slow. when the one CPU thread was 0.7 milliseconds. That's not exactly efficient use of the GPU. So how to make it faster? So you already have mentioned some ways to do it. So I think it was Jonathan mentioned collapsing the loops. So let's go back here, okay, and let's collapse the loops. Now, when we do this, essentially here, when we so if you don't have collapse, you're only distributing over the first loop. Now, this grid is 500 by 500. So that means that you only have 500 tasks. So without collapsing with a second loop, here you only have 500 different tasks. And on IMA 210, you can run up to, you can have up to about 200,000 threads on the GPU. So that's not enough to fill the GPU. You're only using a very tiny fraction of your device. So what if instead we collapse with an inner loop? So let's do our quick calculations. So with only parallelizing the other loop, we have 500, about 500 loop iterations. How many tasks do we have? Well, on the, so how many tasks can we fit on the GPU? Well, so we have 100 on MI210. We have 104 CPUs, computing units, and each one can handle 32 web front, and each web front is a pack of 64 threads. Okay, so that's 23, about 23%. So at most you can use 23% and about 20% of the device. So what if we merging with the outer loop? So then the number of tasks would be 500 times 500. Okay, that's the total number of grid points. And okay, that's 100 and about 120% of what you can fit on the GPU, which is great. The more the better. Okay, so this should be able to fill the GPU if we add collapse. Let's try and see if that's correct. Let's recompile, run it. Okay, this is 10 times faster. It used to be 0.4. So now it's suddenly become 10 times faster to run on the on the computing kernel. So, and this just by adding collapse too. Okay. So essentially what this means is in order to get even acceptable performance on a device, you need to have enough parallelism. So this is you need much more parallelism that you would on the CPU. On the CPU, as long as you have one per core, is fine. Quick question. So is collapsing loops a similar concept to unrolling loops? Yes and no. So when you unroll, so unrolling loops essentially helps, essentially means replacing all the iterations with a, instead of writing the loop, you explicitly write multiple times all the iterations inside the loop. So this is not the same as, I wouldn't say it's the same as collapsing the loop. Collapsing just means when you submit task to the GPU instead of so if you don't have collapse, you only distribute the task you're distributing to threads. It's only what's inside this for loop, outer for loop. So that means all of this. Okay. So all of this for loop gets sent to a thread. So each thread runs a for loop over the index E. And if you have a collapse clause instead, what it does is to every thread on the device, it sends this. Okay, so no loop. There are no loop. You might think of it as a rolling, but it's not actually generating, it's just sending the loop iterations in a different way. So without collapse, it's sending all the loop iterations to one thread. While with collapse, it will send to it won't send a whole loop. It will just send one iteration. So in a sense, you might think it's similar to loop unrolling, but it's a bit different here. This is more who you send to what. Or you map loop iterations to threads. Does that answer your question, Jonathan? Perfect. Okay, so we've seen now this is much faster. However, there is a way to make this much faster. So the issue was we've seen when it's very important to have successive threads on a warp access contiguous element in the array. Now we're assuming a C-style ordering, which means the second index, so the J, is the one that runs fastest, which means the element at J and the J plus 1 are contiguous in memory. Now, what OpenMP does is when you have multiple loops, is that it takes the outer loop, the inner loop, and spreads them across contiguous thread. So the iteration with E equals 0 will probably be the same as the iteration on E equal 1, on the same work as the iteration at E equal 1, 2, and so on until 64. So what we have here is that successive threads will access elements with different E, and in C that means they're not contiguous in a memory, they're threaded by the number of elements you have in a row. Okay, so you're doing a threaded access. So we think that this is bad because it means that you're doing much more load instructions per web front than you should. So you can't collapse all the memory accesses. So what we can do is take this and swap it. So very simple change, we just change the ordering in the loop. Okay, I think this is correct. But let's see. So I'll recompile, run it again. Okay, this is suddenly got much faster. So we 0.0.5 and we're now 0.025, so factor 2. So it's twice faster just by swapping the orders of the loop. So now, so now at this point we're much faster than one CPU thread, so we're making a more efficient use of the device. However, what do you think could be limiting our performance at this point? So the kernel now is fairly fast. It runs in 25 milliseconds. So each offloaded regions runs in 25 milliseconds. What do you think could be the bottleneck at this point? So we're sending a lot of parallel regions, and the parallel regions are really fast. Okay, so we kind of done a kind of a good job at with bandwidth. So we're sending a lot of stuff, and everything is running very fast. So bandwidth seems okay. We're doing efficient memory accesses. So probably not the bandwidth. What else could it be? So bandwidth is the first thing you should always look at, and we've kind of addressed this by making sure there's enough parallelism, so enough occupancy on the device, and making sure that we have efficient memory access. Well, we actually do not seem to get all the performance we could get. So GPU devices have very high bandwidth, but low latency. And we have the parallel regions are now really fast. Okay, 25 microseconds and they're done. Okay, perfect. Thinking between interactions at this point. In a way, maybe. So you're right. The problem is synchronization. So every time you run the kernel, so you send it to the GPU, and you have to wait for it to finish. Okay. But sending a kernel to the GPU takes time, and because this takes time, it's not a lot of time, but you still it needs time to send all the data to all the iterations to the device. Okay, they have high latency. So roughly on memory to engine 10, that takes about 10 microseconds. That's about half of the time it takes for this computing kernel to run. So we've done such a good job at optimizing for bandwidth, but it runs so fast that the time to run it is about the same time it takes to just offload the parallel regions to the device. So what here it's limiting you is kernel latency. Basically, there's not enough. There is enough parallelism, but not enough work inside the kernel to make it run fast. So yes, Lian, in a sense, it's similar to synchronization, but not on the device, more between the CPU and the device. Okay, I think this is all I wanted to show you today. Does anyone have any more questions? So when you're in the end of the course, so could be about exercises or anything else. This is a good time to put questions. Perfect. So this said, I would say we can end the session here.